Theorem 4. If f and g are continuous at a and c is a constant, then the following functions are also continuous at a. I'm just going to use the first one to prove. So in order to prove f plus g are continuous, then we need to show that the limit of f plus g equal to f plus g of x. Okay, so because we have the sum, then we can break this down using the first law, right? And then we know that the function f is continuous, the function g is also continuous at a. This is given from the theorem. Then we can write limit when x approaches to a of f of x equal to f of a, and limit of g of x as x approaches to a is equal to g of a. So we can write f of a plus g of a, and is equal to f plus g of a. Then we can conclude that f plus g is a continuous function. Theorem 5, Part A. Any polynomial is continuous everywhere, that is, it is continuous on the R from negative infinity to positive infinity. Let's assume that we have a polynomial function Cn x to the n plus Cn minus 1 x to the n minus 1 plus C1x plus C0. For C0, C1 all the way to Cn are a constant function. Then we take the limit of the p of x. Okay, after we take the limit of p of x, we can separate them. And also the cn minus 1, that are constant, so we can move it to the front. So we got the limit of a power function. And we use law number 9. We just plug a to the x, so we get a to the m. So this implies that x to the m is a continuous function. If we have the number in the front c of f of x, it will be a continuous function also. We are using the number 3 in theorem 4. Okay, so each of this is continuous function, and C0 is a constant function. This is also continuous. So P of x is the sum of all continuous functions. So we can conclude that the polynomial function is a continuous function. In part B, a rational function is continuous everywhere whenever it is defined, that is, it is continuous on its domain. We have the rational function in the form of px over qx, for px and qx are polynomial. The domain of the function f is a real number except for the bottom qx not equal to 0. Since px and qx are polynomial, they are continuous. We got this from part A, because polynomial are a continuous function. So, and then we combine number 5 in theorem 4. A polynomial function divide another polynomial function, continuous function divided by a continuous function. We get a quotient, and that quotient will be a continuous function also, as long as it's not in the domain.